Good afternoon, Mario and Cameron.
Hi, how are you?
Good, how are you?
I'm good, thanks.
Hello.
Hey, Mario. And you guys at home or at the school or on campus?
I'm at home.
Yeah, same.
Yeah, how many classes do you have on campus this semester?
1.5.
1.5. I see. How about you, Cameron?
Yeah, same kind of because I have recitation on Fridays that are in person.
Oh, I see. That's the half. Yeah, it's kind of weird with with half of the class on campus.
Yeah.
Yeah, let's wait a few minutes for more people to see if more people will come today. Hello, how are you, Juan?
I'm doing pretty good. How are you today?
I'm doing well, thank you. Hello, Jerry.
Hello, Professor.
How are you doing?
Okay.
Now, if you don't mind, you could feel free to turn on your camera. You can always turn it off when you need to. All right, find it that it's easier to keep us focused if our camera is on. Hello, Iwan. Can you hear me? Seems like he might still be connecting. Hi, Iwan. Can you hear us?
Yeah,
Are you?
I'm good. How are you?
Good, good. Okay, all right. Just 1 second, please. We will finish our review today. And starting on Wednesday, we will do complex circuits, which is sort of a subsection in chapter 7, but we didn't really do that in the last semester, sort of treating it as a new topic. All right, so to continue with our discussion from the previous week, we had reviewed electrostatics, and we had pause and do a little bit more questions and on the boundary conditions. Do you guys still remember all the boundary conditions that we have derived so far? So let's review them. So simply just doing 1, 2, 3, and we're just going to continue to list all the boundary conditions you remember. Anybody remember any of the boundary conditions we derived previously?
We have E perpendicular above minus E perpendicular below is equal to sigma over epsilon naught.
Okay, very good. Thank you. E above perp below minus E perp below is sigma over epsilon naught. Excellent. And anything else? Any other ones?
E parallel above is equal to E parallel below.
Yes, E parallel above is equal to E parallel below. Very good. That is the parallel component of E is always continuous across the boundary. But your perpendicular component could jump, especially if you have a surface density, charge density across the boundary. What about the boundary conditions for the potential?
The potential above is equal to the potential below.
Very good. Thank you, Cameron. The potential is always continuous across the boundary. We also talked about the boundary conditions for the displacement field. Do you still remember what that looks like? So D.
D perpendicular above minus D perpendicular below is equal to the sigma free.
Okay. equal to sigma free. Very good. And this sigma, what is this sigma for the first boundary condition? Is this also sigma free?
Is it total? Is it sigma total?
Yeah, this one is sigma total. So you might have sigma free and you might have sigma bound, bound charges when you have polarization. But the D is only the sigma free. Very good. The very last one is a parallel component for the D, which is the same as your polarization, parallel minus polarization below. Okay, so we have done all of these. Today, we will look at the boundary conditions for the B field. We will start out with a question. So we know that this is really one of the Maxwell equations. There are no magnetic monopoles, right? So the flux of B dot dA is 0. So if you look at, we're talking about NS, right? If you have a magnet, the magnetic field lines are sort of going enclosed, right? It's like a closed loop. So if you look at the flux around a closed surface, you always have equal number of that field lines coming in and equal field lines coming out. So the total flux is 0. So which one of these or two of these that is equivalent of saying the same information? So I'll let you guys go ahead and have maybe 1 or 2 minute discussion within the breakout room, and then when we come back, we could have a discussion together. So it seems like we only need the 2 breakout rooms, so I will just go ahead and open up the rooms. You can take a screenshot of your picture, so you have the question when you leave to join the breakout rooms, okay? All right, so maybe just take a couple minutes to discuss. Sorry, let me get back to my share. You need the question. All right, did you guys join the breakout room? Room 1, still nobody's there yet. So go ahead and accept the invitation to join. Brendan, have you joined the breakout room yet?
Hey, can you hear my microphone?
Yes. Something-
I drove to class and I'm now on the Well, I'm about to drive back.
Okay, sorry, you forgot that we are meeting online this week. Okay,
It's lagging a little bit. I'm using cellular.
okay, no problem.
right.
Yes, I did assign you to breakout room 1.
Thank you.
Okay, no problem. All right, so go ahead and put your vote for this question, please. Okay. All right, so it looks like you have all unanimously agreed on number choice E. One is simply the differential format of the Maxwell no name law Maxwell equations. What about 3? So 3 is apparently another boundary conditions that come from this derivation. So to derive these boundary conditions, can anybody tell us or share their thoughts? How should we set it up? Like what kind of picture should we draw in order to derive number 3? So from here, how did you get this one?
You probably draw like a closed surface, like a Gaussian surface.
Okay, I would draw a closed Gaussian surface, and across this boundary here, I'm going to draw a boundary. And what kind of what should I have at the boundary? Should I have some current as my source, right? So I will have some current density. Okay. So just like if I had a boundary for charges, here I have a boundary for currents, and do a Gaussian surface. Very good. So I'm going to do that. I'll draw a little cube. So draw like a small box. Okay. Now, if you're looking at the perpendicular component of B, that would be B perp above and B perp below. So to expand the left-hand side, you have the top and the bottom surface, right, which will become B above perp above times area A minus P B perpendicular below times area A. And that would equal to 0. Okay. So that you get 3. So yes, E is correct. This is another boundary condition. So let's put it back to the list. I'm going to call it number 6, for example. So B perpendicular above is equal to B perpendicular below. So this is telling me the perpendicular component of B is continuous across the boundary. All right. Now, next question has to do with the parallel component. So again, I have a boundary sheet, and I would like to learn about whether it will change or whether it will be continuous. So either way, I want to know what is the B parallel at the two sides of the boundary. How does it change or not change across the boundary? So to know the B parallel, am I going to need to know about curl of B, divergence of B, or something else? So for this one, let's go ahead and do our vote here. All right, do I have all your votes? Okay, now I do. Let's take a look. Okay, so your result is half and half. It's still sort of thinking. I can't really share my screen, the votes with you right now. But half chose for curl, half chose for the divergence. So if we want to know the parallel components, how do we decide whether it's the divergence or the curl? We had already used which one? The divergence. So a good guess would be we need the other one. So let's see what the other one will give us. If I chose again to draw a sheet of boundary, this is the direction of the surface, right? And I will have some kind of a surface current running through this on the boundary. So the reason I would say I would need a curl is because of the looking at the curl, right? This is mu naught J, and using the Stokes theorem, I can rewrite this using the line integral. So if I integrate both sides, the A is mu naught J dA. This actually becomes what? The closed line integral of B dot into dl, right? So that's why we can, when we see a curl, we know that we can evaluate a circulation of the vector field. That becomes mu naught J dot dA is current, I through. Okay. So to know the parallel component, we need the curl because the parallel component is relying on the parallel to a loop. So here, this is the parallel above. You may have it be parallel below. So we will draw a sort of a closed loop cutting through the boundary. And it is very small and narrow with a very small height delta. Right, so you're going to draw a circulation along the loop. So this had become the parallel above times length L. So this is length L. Or to make this in the same, I'm going to use a different color. Let's do it circulation this way so that the choice of the above parallel is the same as my choice of the integration. So minus the below times L is equal to mu naught I. Okay, so here my current is running perpendicular through some length L, right? So this is the sheet. If I redraw it this way, this is my current. And this is the loop I draw. So this is perpendicular. This is perpendicular. So current I is K times L. Okay, K times L. So I can get rid of this L from both sides. And I derived the boundary conditions for the parallel component of B. Was mu naught K. All right, so this will make it to the list. Number 7, the parallel above minus the parallel below is equal to mu naught K. Mu naught K. All right, so you can see that this direction, the parallel component is in which direction? The parallel component B is in this direction, and that direction can be represented by K cross N. Okay, so K is in this direction. So if you think of this, if this is your X, this is your Y, N is your Z, right? So the X direction is a parallel component, can be derived, can be represented by the Y cross Z hat, right? Y hat cross Z hat. So sometimes people write this using a vector notation saying B above minus B below is equal to mu naught K cross N hat. But it does not really, it's not a new boundary conditions. It's just a different way to write this if you wanted to include the direction for B here. Okay, so we have derived 7 different boundary conditions. Okay. So next, we wanted to, so previously we did the E and then we did the vector, we did the potential V. And now we need to do the same thing. We did the B, we need to do the vector potential A. Before I move on to do vector potential A, are there any questions on these 2 boundary conditions so far? Any questions? Okay. All right, so that was the results, by the way. It finally stopped. So let me go ahead and open up this question. So in terms of what might be continuous as we move past the boundary, remember we had V above is always equal to V below. But now instead of V, we have vector potential A. So how does A compare, A above compared to A below? Do you think all of the A is continuous or maybe just the parallel component of A or maybe the perpendicular component of A? So that we do, I do want you to have a discussion on this. So take a screenshot. And I'm gonna open up the breakout rooms for us. Okay, in a second. Okay, so the number of person is a little bit uneven, so I'm gonna have to move it so that it's 300. I'll give you a hint before you go ahead and discuss. To do the parallel perpendicular component, right? You need to think about to get the perpendicular component, you probably want to think about the divergence, okay? And to get the parallel component, you want to think about the curl of A, okay? So for the divergence, again, we could assume that we are working with Coulomb's gauge. So you have total freedom of your gauge choice, and we're just going to do Coulomb's gauge. The divergence of A is 0 here. Okay, so that's just some hint. So I'll let you go ahead and have a discussion, and then we can work on it together. So what do you guys think? Any discussion?
A perpendicular above is equal to a perpendicular below for the same reasons as
Okay.
before the magnetic field.
Okay, very good. And then what about the parallel component?
Well, they're not equal because the curl is equal to B, the magnetic field, and similar justifications for the fast boundary conditions will show that they're equal to some sort of quantity.
Yeah, so okay, so for the curl, I encourage you to go ahead and try to write something on your paper, or if you wanted to derive on the board with a screen share, that's fine. So in order to give us the parallel component, what we're really getting at, we wanted to A dot into DL, right? So from here to here, we need two steps. We need to integrate both sides, and then we need to use Stokes' theorem. So see what you will get from here to here, and see what would A dot into DL will equal to. Right, I will see you guys when you get back to the main room, okay?
Okay.
Definitely one of the first two ones.
Yeah.
I mean, I feel like I can't remember.
think it's just perpendicular actually, because
Yeah,
are all supposed
yeah,
to be boundary conditions, right? So if B has a boundary condition, then
yeah. I think it's just perpendicular because B is like there's some difference between the top and the bottom of B, and the curl of A is just B.
yeah,
So yeah, I agree. I think it's just perpendicular.
cool.
Sweet. What do you think, Cameron?
I'm not entirely sure, honestly. I'm still kind of trying to wrap my head around it. I guess yeah, what you guys said makes sense. So
All right, please go ahead and put in your vote for the question. Okay, all right. Let's see. So it looks like we all agree, and all of you agreed on the one of the components, right? So there's only two components of a perp or a parallel. So you all agreed on the a perp, right? Which is a perp is derived from this, and that is equivalent of saying a dot the a is 0, the area is 0, and that is equivalent of saying a perpendicular above is equal to a perpendicular below. Okay, very good. So what about the parallel component? I did give you a hint that we may want to look at what the curl of A is, right? So the curl of A is B. So how do we further process this?
What I did, or what I was thinking, was that since the curl of A is equal to B, then I just looked at the two components of B, but we already had that B above equals B above perpendicular equals B below perpendicular, so I didn't need to worry about that one. So just looking at B parallel above minus B parallel below,
Okay,
that's non-zero.
okay.
And I wasn't sure initially whether or not that meant it was not continuous or it just had like some sort of gradient. And so when I looked back at the displacement So for D, when there was no free charge, the perpendicular components were equaled 0 when you subtracted them, and then it was continuous. But when it was non-zero, it wasn't continuous. So I thought that the parallel component of A wouldn't be continuous for that reason.
Okay, so we try to extract the parallel component from the curl. Very good. So how exactly would the next step be? Anybody else would like to share their thoughts?
You can write the surface interval.
Okay. Okay, something like that.
Yeah. And then rewrite the left using Stokes' theorem.
All right, so doing the Stokes theorem. For the left-hand side. So would this become ADL then?
Yeah.
Okay. All right, so if it's ADL, we all agree that we're trying to extract the parallel component of that. So it will be A parallel below minus A parallel above, multiplied by L. But eventually, we will want to cancel out the L. So I'm just going to sort of get rid of this L for now. Okay, what do we do for the right-hand side?
Isn't it 0 because of like we could apply the divergence theorem to it, and we kind of stated it above that.
So as long as you can make the flux of B go to 0, then we can make the A to be continuous. So you're right in the sense that the right-hand side, the B dot into dA, as long as we can make the flux of B go to 0, we will be able to have a continuity for the parallel component of the A as well, so that the parallel and both the parallel and perpendicular component are both continuous. So we can have A to be continuous across the boundary. All right. Obviously, for the divergence A, that is a choice of Coulomb's gauge. So you can have an A that is not continuous. It's possible. But if we choose the Coulomb's gauge, we can have that component. We can have our A to be continuous across the boundary. To rewrite this in terms of the derivative of A, so remember we had V above is equal to V below. Okay. We can also have A above is equal to A below as a vector. We can rewrite V in terms of, change E in terms of V as dV dN. So we can also make this into dA dN. All right, so it becomes dA above dN minus dA below dN is equal to negative of mu naught K. Okay, so this is equivalent to the boundary conditions for B, but this is not new. This is represented using the information for the potential. Well, there is a little bit of a derivation here. So let's take a look at the derivation. So how do we go from B above minus B below to the derivatives of A? So let's draw a little picture to help us. If we have the X and Y component like this, Y and X and Z, okay, and then I'm going to draw my current K in this direction. So if I have my B parallel drawing like this, B parallel above, that is in the X direction. So since my A, still remember the A, right, is K, the area over script R, right? So A is in the same direction as K, right? So if A is in the same direction as A is also in the Y direction. So if I do the curl of A, so that becomes I hat, J hat, K hat, D dx, D dy, D dz. A only has a Y component in this case. Okay, so that's AY. So that will equal to, you can see that equal to I hat negative day dz. And curl of A is equal to B, right? Because equal to B. B is in the X direction. So it's going to equal to BX I hat. Okay. So since the B above minus B below is mu naught K, which means dA above minus dZ, dA below dZ is going to be negative mu naught K because you have a negative sign coming from here. So A, if you move your A in the X direction or Y direction, you're not changing your value for A. If you have any change in your in your A, it will be confined to the normal derivative. It will be respect to the Z direction, which is perpendicular to the boundary. So you can see that's why we can rewrite your dz using dn hat, because my boundary, this n hat, is the Z direction. So that's why we have another similar boundary conditions that's very similar to what we had previously. So if I would allow me to add this to our list, it's not a new one. So 1 prime is dv dn minus dv dn is equal to negative sigma over epsilon naught. So 7 prime is dA dn minus dA dn is equal to negative mu naught K. Okay, so you can have the 1 prime and 7 prime, but it's not new. So if you're just counting boundary conditions, I would say, okay, we have 7 of these. All right. So before we do further of the questions, I want to continue with our review. We had E&M in matter. So now in matter, when you have, previously you had polarization. Here we have magnetization. Remember, we had defined magnetization to be the sum of little magnetic moments over the volume. We also said the J total will be J free plus J bound, where the J bound is simply is a curl of magnetization. So that was our chapter 6, right? We had done that previously. So this equation has changed its format, mu naught J. J is now free plus bound. So the curl of B, so I'm gonna put the curl together, minus mu naught M is equal to mu naught J free. So if I divide mu naught from both sides, right, I get this new quantity, and we call that the H field. We give it a new name. Just like our displacement field for the electric displacement field, this is a H field for magnetization. So the curl of H is equal to J free. So remember we had this sort of this is your Maxwell equations in matter, right? So you probably have already figured out this will give us another boundary condition. Again, at this point, I hope that we are very familiar of how to derive the boundary conditions. Is when you see a curl, you know that you will draw a cubicle, you will draw a little cube across the surface, and you're going to get a perpendicular component. Okay, so sorry, when you see the curl, you will get you will draw a line and you get a parallel component. I get it reversed, and I apologize. Okay, so for this, again, you will have H dot into DL is current free. So this will give H parallel minus H parallel below. And the direction is not that obvious to see. So I need to draw a little picture. Draw a little picture to show my current. And this is my L. Okay, so above L minus below times L is equal to the current that's running through the surface. So you can see this is a current K, and it is running across a perpendicular cross length as L. So you can put L here, right? So you could just simply say H above minus H below is equal to K. Now, if you do want to add directions, and sometimes people do, you have to see, okay, if H parallel is a vector, in what direction is that vector? You can see that parallel component is in this direction, and that is the direction of K cross N hat, just like what we did previously with our B, right? This direction is the same direction as your K cross N hat. So we can also rewrite this K cross N hat. Or not, or you just use a magnitude and use a magnitude of K. That is also fine. All right, so we even have space for this to go back to our list, put everything in there on their same page. This will be, well, actually the 8th boundary condition is the A below, above, it's A below. The 9th is the one we just derived, H above minus H below is K free cross N. The last one, okay, I promise this is the last one. No more boundary conditions. The last one is my perpendicular of H, and I need the divergence of H. Okay. So the divergence of H is the divergence of B over mu naught minus M, because that is the definition for H. And you can see that, well, the divergence of B is 0. So that really just going to be decided by the divergence of M. So the last boundary conditions simply is not really all that informative. It's just simply saying the perpendicular component of H, the change across the boundary is going to be the same as the magnetization's change across the boundary. You have a negative sign. So this is the last one, number 10. I'm not going to put it up. I'm running out of space. But that's all. That's all the boundary conditions. We're finally done with all of that. Okay, so next I want to move on to talk about a little bit of chapter 7 and Faraday's law, and then we will do a little bit of neutral inductance, and that will conclude our discussion with our review. Go back to chapter 7. Chapter 7. Okay, chapter 7, we have a very important law, which is worth to review here because chapter 8 is a conservation law. So let's review what is charge conservation. So what is charge conservation? Charge conservation says if you have a change in charge, dq over dt, if that changed, which means that must be equal to the charge flowing out or flowing into the surface, right? So if you charge flow out of the surface, then your charge differential space must be decreasing. So dq dt must be negative of whatever flowing out, right? And vice versa. If your charge coming into the surface, then your charge will increase here on the other side and your flux is negative, right? So negative, negative give you a positive increase. So dq over dt is negative j dA. That is simply charge conservation. But charge conservation is rewritten in the slightly different format because we wanted to write this using density rho. So Q becomes the integral of rho dt. So it's dq becomes d rho dt times d tau is equal to the total current that's flowing out of the surface. So that's equal to negative j dA. And I'm going to rewrite this using divergence theorem. That becomes what? The integral of the divergence of j times d tau. So now you can get rid of the d tau for both sides. And we get our charge conservation, which is d rho dt is equal to negative divergence of j. So that's charge conservation. There are a lot of very interesting conclusions we get from charge conservation. For example, combine that with Ohm's law, which is sigma j is proportional to sigma E. Now this is very interesting. Now E means that you have let's say if you have a constant push, you have battery, which produce a constant push on your charges. That gives you a constant. So these are proportional, which give you a steady push, give you a steady current. Right? That if you think of those in terms of classical mechanics, that's weird because a steady push will give you the charges will be moving faster and faster. You might have a current that's bigger and bigger, but it's a constant push. I'll give you a constant field. I'll give you a constant current. That's because there's a lot of collisions. When your electrons get pushed to move, they at the same time encounter a lot of collisions. That's why overall the current is still steady. So this is microscopic Ohm's law, which is so this can be derived the one that we measure in our lab. Macroscopic Ohm's law can be derived from the microscopic Ohm's law. So these two, they're the same actually, even though they look different. Okay, so combine this with this, you'll get some interesting results. For example, if I do this, if I say for a steady current, the charge will not be built up, right? Meaning that steady current is like a steady flow, like people pass through the hallway, enter into the different rooms. People are not lingering around in the hallway. So whatever comes in continue to exit out of the hallway. So you have a steady flow. So there's no people built up. In this case, is no charge is building up. So if charge is not built up, what is d rho dt? D rho dt is going to be 0, right? So if d rho dt is bigger than 0, which means the charge are collecting and building up in the space, that is not. So if d rho dt is 0, use charge conservation, you get divergence of j is 0. And again, use Ohm's law, you get the divergence of E is 0. And again, we know that divergence of E is equal to rho naught over epsilon naught, rho over epsilon. That's Gauss's law. So, and we get rho is 0. So that just tells me that the current density inside a steady flow is 0, right? So even if you do have positive charges here, you have electrons here, but if you're looking at the overall density, it's very homogeneous, right? It's not like you have more positive charges than you have for negative charges. they are equal. So you still have a 0 overall charge density inside a steady current, a steady flow. Okay, so that's maybe counterintuitive because when we think about current, we think of a lot of charges moving. So how come the density is 0? Density is still 0 inside a steady flow. So that's what we did in chapter 7, right? We talked about charge conservation. A very important aspect in chapter 7 is Faraday's law. So let me add each here. Okay, so let's continue. So for Faraday's law, we start out with motional EMF. Motional EMF is generated associated with motion. So if you move a metal bar inside a magnetic field with some velocity, the voltage generated across the two sides of the metal bar. So this is the voltage. This is the voltage generated is B times L times V. Now, if you had connect this with some ammeter, you're going to read some current here. But if you don't have a closed circuit, you're just going to have a voltage across the two sides. It looks like you have generated yourself a battery. More generally, this voltage is associated with motion, but more generally, as Faraday pointed out, is associated with induction. It's induced EMF because you don't always have to have motion. You can turn your B field on and off, have a change in magnetic flux, and you'll have the same result. You have same effect in terms of generating EMF. So, and more generally, you can write EMF as in change of flux over time. Okay, so what does this one look like? Let's further expand the left and right hand side. So this is really essentially Faraday's law. Why is that? Because this is voltage, and voltage is E dot into dl, right? Voltage is E field integration over a loop, over some path. And I can rewrite my flux using B dot into dA. So this is the Faraday's law that you're familiar with, right? And if you simply use Stokes' theorem again, the left-hand side becomes the curl of E dot dA. The right-hand side is still B dot into dA over dt. So if you do use Stokes' theorem on the left-hand side, you can get your differential format for Faraday's law is curl of E is dB dt. Okay. So this is Faraday's law. And the meaning of that is if your B field is changing with respect to time, you will have an E field. A changing B field produces an E field, right? And the negative sign here, very important. The negative sign simply tell you Lenz's law that nature is always trying to oppose that change, right? So if you try to increase your B field, then you will induce an E field, you will induce a current that is trying to produce a B field that's opposite in the sign. But if your B field is decreasing, then your induced B field will try to stop that change, will try to produce a B that's in the same direction as the original B field. So that's what the negative sign is telling us, is nature is always to oppose the change, not oppose the B field itself, but try to oppose in which way it is trying to change. So if you try to increase it, it's going to give you something opposite. If you try to decrease it, it's going to give you the same direction. So basically that's what it means. All right, let's quickly look at a couple questions. And the first two questions can be answered using the Faraday's law or the Lenz's law. All right, so we have two loops, 1 and 2 identical. a one has a current running through it. So it will induce a current in loop 2, and this current in 1 is increasing. In what direction is induced current in loop 2? So I'm gonna go ahead. This one I don't believe we need to discuss. So I'm just gonna go ahead and let you vote. All right, do you have more votes? Okay, all right. There's a unanimous agreement on choice B. Okay, anybody would like to run through the logic for us? So given this I is increasing, how do we figure out the direction of the current in 2? So anybody would like to run through the logic for us, please?
Just using Lenz's law,
Okay.
the induced current, because loop 1 is the current in loop 1 is increasing, you would want to oppose the change, so you would want to do the opposite thing.
Okay, so original current produced a B field pointing upward, and that upward B field is also increasing. Very good. To oppose that change, you want to produce a B field downward, and that is corresponding to a induced current in the opposite direction as your original. Very good. So induced will be this in this direction. Now, what if I put loop 2 to the side? What will happen there? That one, I will give you a minute or two to discuss, and then when you come back, we can vote on this, okay?
Hard to do this without a picture, but
You mean like it's like that?
yeah, like big, kind of like a dipole
Yeah.
looking. So they'd be going down at that point, right? The field lines.
Yeah.
Mhm.
Okay. All right. So I have everyone's vote. Let's take a look. Okay, so to see whether everything else is the same, I current is still increasing. You realize if the answer were any different from the previous one, it has to do with the B field of the B field that's going through 2 due to loop 1, right? So at the location of loop 2 is new location. What is the direction of the B field?
Down.
Overall downward. Yeah, very good. This is a current, and you will have your B sort of going like that. And you can see overall in the location where loop 2 is, if B is going down, and downward is increasing. To oppose that change, you want to produce a B that is up. So you actually induce the same direction as your original current. So it really depends on the location of your loop as well. Very good. So A here would be the correct answer. Now the last one on this topic is what if I simply rotate loop 2? So they're not really side by side. This is where they were side by side, but I rotate one of them, but it's perpendicular to the original one. What happens now? If you would like to go ahead and enter your answer for this one. Knowing that the loop 2 is perpendicular and it's not shift away to one side, it's exactly at the center of loop 1. Okay, so it's sort of in the middle, not all the way here or here. That is also important in terms of the answer. Okay, any other more votes before I close? All right, so if I ask you the same question, what is the direction of the B field at the location of 2 right now? What would you tell me?
Down.
It's also down. Very good. However, what is the flux through loop 2?
0.
Very good. It's 0 because the orientation of B down, A is actually is this way, right? B is down. It's not going through the loop. Only when your loop is flat, you can have B going through the loop. Right now, loop is parallel to B. The flux is 0. So if there's no flux and really there is no change, right? If the flux is 0, of course, it does not change. And therefore, it doesn't induce any current. Excellent. So the answer is C. All right. This one, I'm not going to let you vote. I just want to simply mention what it means. When we have solenoids, you can see that is the same current wired in the same direction. So your B will actually be increasing. Now you can, in a lot of times in application, sometimes we want this induced current to be amplified. So we wire this loop in the same direction. Sometimes we actually don't want the induced current. We wanted to get rid of the effect. A trick to do that is you can rewire them in the opposite direction. So the effect will cancel out in each other. So for example, in this case, it will induce some current in 1, but it will not induce anything in loop 2 because loop 2 is wired in the backward direction. Okay, so that's a way to get rid of the induction effect in practice. If you don't want it, simply wire it backwards and you can get rid of the induced current. But we are not going to go through the voting for this one. So I wanted to take a little bit moment next to talk briefly about mutual inductance. The mutual inductance is simply defined to be so you have two loops, 1 and 2, like we were showing you earlier. Then the mutual inductance is equal to mu naught over 4 pi, the integral of loop, two of the loops, doesn't matter which one goes first, dl1, dl2 over script r. Okay, so r is pointing from one of the segment in 1 to one of the segment in loop 2. So this is totally decided by geometry. So you can see that if you want to think about the flux it generates, you can think of, okay, the flux going through loop 1 is due to the current in loop 2, and that is multiplied by the mutual inductance 1, 2. But the flux going through loop 2 is generated by the current going through loop 1 and multiplied by the mutual inductance in M21. Okay, so depending on the geometry, sometimes it's easier to calculate one of them, but these two are equal. So here M12 is equal to M21, as long as you have, because you can see DL1 and DL2 are both factored in this calculation. So these two are equal. Mutual inductance is equal. It's sort of giving us an idea of the physical setup. So the sort of the ability of how much induced current you can generate given this setup. So it's a description of a geometry of which you have. But it's not always equivalent to calculate. Sometimes it's easy to calculate one first, sometimes it's easier to calculate the other one first. So if I want to calculate M12, what do? M12, I would use flux 1 divided by current 2. If I want to calculate M21, I will use flux 2 divided by I1. So with this setup, 1 is some random shape of wire and 2 is a solenoid, is a long solenoid. So which one of these is easier to calculate? M12 or M21? If you do M12, you will do flux through loop 1 divided by current 2. If you want to calculate M21, you do flux through loop 2 divided by current 1. So which one is easier to calculate? And you don't have to vote since we're running out of time. So if you would like to just say your thoughts or type your thoughts, any of those would be appreciated. Any thoughts? So if you were to calculate either one of them, which one do you think is easy to calculate?
Probably 2, 1.
So this one. So this one, you need the flux through 2. How do you get the flux through 2? You need the magnetic field generated by 1. So flux through 2 will be the B due to 1 times the area of 2. If you want a flux 1, that is a B due to 2 times the area of 1. So which one is easier? Area is all easy, right? What's difficult is the B field. So is B due to 2 easy or B due to 1 easy to calculate?
B due to 2.
B due to 2 would be easy because that's just a solenoid. B due to 1 is hard as an irregular shape. So when we say flux through 1, meaning that, well, the flux is due to something else. So the flux through 2 is from 1, not 2 itself. Okay, so that because we're doing the mutual inductance here. So that's why this one is actually a little bit easier to calculate. Even though all of these can be calculated using the geometry, but if you want to do the flux, then sometimes it really depends on the whether the configuration is a random shape or something that we already know what the B field will look like. So M12 will be easy to calculate. All right, so that's just a little bit touch on the mutual inductance, and that wraps up with all our discussion on our review. So starting Wednesday, we will be doing complex circuits. Okay, and we will spend hopefully two class time on complex circuits before we move on to chapter 8. All right, thank you for everyone for joining the Zoom meeting today. I'll see you one more time on Wednesday online, and back on Monday, I'll see you guys in person. All right, have a good rest of the week, and I'll see you on Wednesday.
Thank you, Dr. Ryan.
Thank you.
Would I be able to see the mutual inductance equation again?
Oh, yes, of
Put
course.
it down.
Is it not shared anymore? Yeah. You mean this one?
Yeah, I just didn't miss that. Thank you.
Thank you. I'll see you
Have a
on.
good day. Bye.
Thank you. You too. Bye-bye.